Okay, good morning everyone. Thanks for watching this video. So we'll continue our lecture and to finish up this nonlinear linearization part of this course. So through the discussion of the last previous few lectures, we have covered the material on how to linearize a nonlinear system by locating the equilibrium that you're interested in, which may include both the output signal and your input signal, and perform the Taylor series expansion either on the differential equation or upon the state space representation to eventually obtain the linearized system. And we discuss several examples and illustrate how this can be done. And today in this particular part, we're going to discuss how we can determine stability of the nonlinear system by looking at the stability of the linearized ones. And just to refresh the memory, when we talk about stability of equilibrium, there are usually three types. Asymptotically stable, meaning when you move away from this equilibrium, without additional work, the system will come back to this equilibrium asymptotically, meaning in the long run will return back to this equilibrium. And unstable, meaning if the system move away from the equilibrium, then it will not return to the same equilibrium anymore. It can move to another equilibrium. It may blow up to infinity, but it will not return to the equilibrium where you start with, where you start around. And the last one is marginally stable, meaning while you move away a little bit from this equilibrium, you will still move in the neighborhood, but will never come back. That's the marginally stable. Okay. And so the question is, how do we do the determination using the linearized system? Now, as an example, if we still look at this pendulum example, we can see that, well, this particular equilibrium where it's pointing downward, this is asymptotically stable, because if you move this away from this position, okay, it will eventually move back to this point if no external force are being applied. But for the other one, if you move a little bit away from this equilibrium, and as long as you let go, apparently this will fall down and eventually will go back to the other equilibrium because there's friction, but will never return. Okay? So it's an unstable system. Now, in general, how can we determine this? Okay? The results of, or the determination criteria used in the linearized system is called the Hartman-Grotman theorem. So Hartman dash Grotman theorem. And this theorem, this result is not included in the textbook, so I want to point it out. So this is not in the textbook. But it's a required material in this class. So make sure you understand it, and we'll be able to use it. So the content of the theorem is like this. Let's assume we have a nonlinear system. For a nonlinear system, S, okay, and consider it's one of its equilibrium, y star, and in the state space it can be x star as well, or it can be u star as well. Okay, no matter what this could be. Okay. Let's, for the sake of completeness, let's write all of them together. So we have a equilibrium. And let's say we linearize at this equilibrium. And the linearized system is S sub linear. Now here's the conclusion. When you have this linear system, you can use the eigenvalue or the characteristic roots from your 3101 class material to determine its stability. And here is the result. There are several cases. If all lambda i's let's assume this with characteristic roots lambda 1 up to lambda n. And if all lambda i's have negative real part, then we know that the linearized system then it's clear that the linearized system is asymptotic stable at this equilibrium, and the nonlinear system S is also asymptotically stable at this equilibrium. Okay, so if the linearized system is asymptotically stable, the nonlinear one is also asymptotically stable. If at least one lambda I has positive real part, then as we know, the linearized system is unstable. And this also implies that the nonlinear system, both of them, are unstable at this equilibrium. Okay. And when we talk about stability, we always have to point out what is the equilibrium you're focusing on. Now there's a third case, right? There can be something with zero real part. If all lambda i's have the real part to be non-positive, but some has zero real part. For linearized system, it depends on whether or not these characteristic roots are repeated or not to determine stability. But since we're looking at nonlinear system, we want to know if that can carry over to nonlinear systems. Unfortunately, this cannot be done. So when this happens, no conclusions about stability of the nonlinear system can be made. Okay. So this is the Hartman-Grotman theorem. You have a nonlinear system. You find out you pick an equilibrium of interest, and you linearize the system around this equilibrium. Now you have the linearized system. You can calculate all its characteristic roots, and if the linear system is asymptotically stable, this happens when all its characteristic roots have negative real part, and this means the original nonlinear system is also asymptotically stable at this equilibrium. If you found out the linear system is unstable with all the roots having or some of the roots having positive real part, then the linear system and as well as the original nonlinear system are unstable at this equilibrium. But if you have some of the roots having zero real part on the imaginary axis, and the rest of the roots are all on the left hand side or in the left half plane of your complex plane, then unfortunately we're not able to come to any conclusion about stability of the original nonlinear system. Okay. So this is the Hartman-Grobman theorem, and we can examine this or quickly illustrate how this can be used, okay, by going back to the pendulum example. So if we go all the way back to the beginning of this lecture, where we have nonlinear system, right? And when we linearize it, we'll have at the two inverted pendulum, the two equilibrium, we have two linear equations, and let's look at what they are. So example. Yeah, let's first look at this equilibrium pointing downward. Okay. So this is y star equal to 0. And at this equilibrium, the linearized system is what? This d square y dt squared plus up over ml squared times y. I'm sorry, times dy dt. Plus g over l times, when you linearize it, it becomes y. Okay. And you can plug in all different values of L or M or alpha. Okay. Apparently all of them are positive numbers, and later on we can show, and usually you can use you can do this to prove this very easily, that this linearized system is asymptotically stable. Okay. Since both roots have negative real part. Okay. In fact, if you still vaguely remember some results from your high school algebra or maybe some calculus class, when you have a quadratic equation, when you have the roots of your quadratic equation, the sum of the two roots will be equal to the coefficient divided by the coefficient here, which is 1, and you add a minus sign. And the product of the two roots will be equal to the coefficient here divided by the coefficient here, and you'll have to flip the sign. Okay. And you can, since you have two roots, they can be both real. If they're both real, their product is a positive number. Their summation is a negative number. Apparently both of them have to be negative. If one of them is complex, the other has to be complex simultaneously. And the two have to be complex conjugates. And the sum of a pair of complex conjugates should be equal to twice their real part, and it's a negative number again. So you can easily prove this. And in later chapters, when we talk about stability, we'll expand the discussion on this. So this is asymptotically stable. Let's look at the other one. The other the equilibrium, we have dy squared dt squared plus the same first order term, and the second one will be minus And here, if you use the same methodology, you find out lambda 1 plus lambda 2 is equal to a negative number. However, the product of the two is also equal to a negative number. Okay? So that means at least one of them have to be negative. And if one of them, one of them has to be a positive number. If one of them is a positive number, the linearized system is unstable. The nonlinear system is also unstable. Okay? So this will be the case for the pendulum. Now we have other equilibrium that has the input signal involved, for instance these ones, right? And you can use the same methodology and to determine whether or not the system will be stable or not. Okay. Apparently it's going to rely on whether or not this guy is a positive number or a negative number. Okay. And what you can easily figure out within this range, this cosine is going to be a negative number. So when this is negative, it's similar to the one before, and it's going to make the system unstable. So this is the Hartman-Grotman theorem. Basically, you look at the linearized system, determine the stability of the linearized system. If it's asymptotically stable, then you're safe. The nonlinear system is also asymptotically stable at that equilibrium. If it's unstable and some characteristic roots indeed have a positive real part, then the system, the original nonlinear system, is going to be unstable. Otherwise, if you have a zero real part roots and the rest are having negative real part, there's no way you can conclude the stability of a nonlinear system based on a linearized one. However, if you take more advanced grad level nonlinear system classes, you'll be introduced with methods that can possibly handle this case by the exact method that can be applied to nonlinear systems. Okay, so this wraps up all the discussions about nonlinear systems and their stability determination based on Hartman-Grotman theorem. Next, we'll start a new chapter, and this new chapter will be chapter 4 of the textbook.